Good morning, everyone.
Good morning.
Always good to hear your voices and see your faces. Maybe if you turn on your camera, then I have someone to look at when I give this lecture. That would be great. Thanks. So, we are continuing on our regression analysis journey for this course in this block. As I told you, the previous block was more about analysis of variance. We've seen all the variants of those analyses. They are actually also regression analysis, but with categorical variables. But this block will be focusing on the regression analysis with continuous variables. We've started out last week with the simple regression, which was actually an iteration of what you've done last year in the statistics course. So today we're going to make the next step into multiple regression. And essentially what that means is that instead of just having one continuous predictor, we add multiple continuous predictors to our model. So we're going to be looking into that. We're going to be building on the assumptions that we have already put forth in the simple regression. There are some additional assumptions that we need to check for multiple regressions. So these are the topics for today, and what I will try to do at one point is, again, just like we've done in the previous lecture and in the previous blocks, to relate this regression analysis to explaining variance, to looking at what parts of the variance are explained by the regression model or the model on its own, and what parts are then unexplained. And we'll try to look at how that relates to what we've been doing with ANOVAs. So that is up for today. So we'll start with just the regression model. So you've been bombarded by Andy Fields in the book with this sentence on top here, where he states that the outcome is always the model plus the error, and that is true for this still. Only this time we are making our model more complex, where we last week had only one intercept and only one slope for one predictor variable. We are now adding more predictor variables. So if you look at this equation, it sounds a bit daunting, of course, because, well, just look at it. But it iterates the same thing, right? So you have an intercept. So that is the point where you're on your x and y axis. If you plot the graph, the b0, the intercept is the place where the y variable, the height of the y variable when x is 0. So it's just determining the height of where your regression line hits your y-axis at point x0. So that's just the same essentially as was done with the simple regression. And then we're just adding more variables again and again. We have a slope, an intercept, a slope for the first variable. So this is b1, the slope that we apply to the first variable, our first continuous variable. And if we add another continuous variable, x2, then, well, that one also has a slope. And we can add even more, even up to, well, you can just keep on adding. Of course, you'll, by just only adding more to your model, it doesn't always explain more. So you have to be careful with that. And of course, here Occam's razor principle still holds, that you try to be sparse with the amount of variables that you try to add to your model. But in essence, this equation just keeps repeating this part for every new variable, continuous variable that you put in here. If you also look at this equation, the betas that I put in here are Greek letter betas, and that is because in essence we're trying to estimate the population parameter, so the slope in the population. And if we take a sample, then we only have our sample data, and we have an estimate of this actual population parameter. So that means that when you write such formulas out in terms of what it is in the population, you do this with these Greek letters. But when you have your data, it is usually done that you use the small letters for the beta to indicate that it's an estimation. And what also holds, if it's an estimation, then it also has a standard error, and of course we use those standard errors to eventually calculate the significance of such an intercept. But we'll be diving into this more during this course, during this lecture. Well, the same thing holds a little bit like we had last time, that if you have a model that predicts outcome, the relation in terms of the correlation between the result of the model and the outcome is an indication on how good the model fits, right? If you have a correlation of 1 between the model and the outcome, then you have a perfect fit. But if your correlation is lower, then you have a less perfect fit. And that correlation, can be transformed, as we've seen, or at least we could square the correlation to get to our percentage of explained variance. But we'll dive into those. One of the most important thing here to notice is that, and I think I've said this a few times before, but this model, it only results in one predicted value, right? Even if you put 100 predictor variables in here, if you add all those together, then, and you, of course, you also have error. If you add all those together, then there's only one number per individual left. So for each actual y that you have for an individual, you have, if you multiply the coefficients and add these all together, you have only one predicted value for the individual. So the indication of y here, the indication of I here is an indication of the index, but you could also think of it of the individual. So the score for this individual is equal to what we predict based on our model. So for the x, for the score of this individual, plus the beta coefficient multiplied by the score for the same individual but on the other variable, etc., etc. So you have one predicted value for each and every individual in your data set. Does that make sense?
Yes.
Yeah. Okay. So in terms of that relation, I've plotted here a few scenarios that you could have. So I've plotted the model prediction, and I've plotted the actual outcome. So what's on the y-axis are the actual scores that we have for the individuals, and what we have on the x-axis is what we predict with our model. And this is just an illustration to visualize the relation between those two, in terms of the amounts of error that you can have in such models. So if you look at this one, the first one, we have a correlation of 0.4. So that's the correlation between what the model predicts, the score that the model predicts, and the actual outcome. And, well, of course, a correlation of 0.4 is not really that high, and you see that also. The red line here indicates a perfect fit, a perfect one-to-one relation between the model prediction and the actual outcome. And you see the spread of the correlation here. It's quite large. So this is not really a very predictive model, and you can see that clearly. So if you were to square the correlation, as I've done here, it will land you the explained variance, and also the explained variance of this model is quite low. Again, this model could contain a lot of independent variables, right? So it's just the sum of all the weighted independent variables plus the intercept. And for this one, well, it's a little bit better. You see the correlation goes up to 0.64. You see that there's still a fair bit of spread around the actual optimal fit. And if we square that distance, then we get 40%, a little bit more, 41% of explained variance. And the more the better the relation between the model and the outcome, of course, the higher the correlation, the more explained variance you have, and the better the fit, the exact fit between the model prediction and the outcome that you even have. Where here I have a correlation that is almost 1 with the predictor the model explaining mostly every bit of variation that you have in your outcome variable. Of course, you don't see these scenarios in real life, right? So there are very few, especially in psychology, predictive models that are so accurate that you can actually, have such high predictive value. So what do you conclude based on such on this relation? So if you look at the relation between the model and the outcome, and knowing that within psychology that even that such scenarios don't happen. Well, they don't actually happen with such a predictive value. So what do you conclude based on this? Can you determine this?
Maybe that there's always some variance explained by something that is not the model. For example, the error.
Exactly. So that could be one thing. But when you say if it is explained by something that is not the model, and you point at the error, then the error is just the unexplained part of course, right? So
yeah.
but that's an important observation, in the sense that the observation and the resulting conclusion is that there is always a lot of error. So even if we have fairly good predictive models, then we will be wrong in sometimes. So, for example, if you try to predict depression based on some predictive variables, so you as a psychologist, you have your patients do a test on these predictive variables, and you see what the predicted outcome, what the predicted level of depression will be. So if you really go on that result, if you're going to be depressed in the coming month because of XYZ, you shouldn't make such conclusions if you don't have a model that predicts very, very, very good. So you have to, the conclusion is if there's error in your predictive model, then you as a psychologist, or well, in any field for that matter, should be careful with the conclusions that you base on those results. I think I've mentioned this topic before in the previous lectures, where we looked at, well, also just the correlation, the scatter plot of the correlation, where I told you that at one point some researchers looked at the relation between language tests at the beginning of university and the actual, well, performance after the first year, and they had a significant correlation, but it was a correlation of 0.3. It was a huge scatter plot. So basing conclusions and determining outcomes based on such, let's say, ill predictive models shouldn't be taken lightly, right? So if you take the model seriously if you act on the model because it has a significant predictor, but you have this amount of spread, it's not a real good predictor. And then you say, well, I'm going to do a language test, and I'm going to disregard these students because they had a low score, and I'm going to only take these students because they had a high score. You're going to miss out. You're going to have students that you actually put into the program that would not perform that well after 1 year, and vice versa. So the main point here is that you should not you should be careful with interpreting the model results, and especially acting on them. So I think that's the main point for based on this relation. Of course, if you have a model that really explains something like this, well, then you are absolutely sure, because then your model is a perfect predictor. But again, this doesn't happen that very often. Does that make sense?
Yes.
Very good. Okay, so we're going to look at some assumptions, and of course the same assumptions hold that do for the simple regression. So the sensitivity we've looked at last week. We've looked at the homoscedasticity. So again, the sensitivity was if there is an extreme outlier, then it influences the entire model. So you should report that and take some measures to take out those outliers. The other one was the homoscedasticity, which in essence is equality of variance across the predictors, and we've seen that you could look at the homoscedasticity by having SPSS calculate the predicted residual, the standardized residuals, and the standardized predicted outcome. And by plotting that, you should have a roundish scatter plot, which indicates that this assumption holds. Again, there was no significant test for this, or any test. It's just eyeballing if the homoscedasticity holds. And Field provides some examples, some plots which clearly show that if there's a deviation from this assumption. The two additional assumptions that I want to mention, and there are more. Field explains quite a list of assumptions that hold for multiple regression, but I've picked these two to elaborate on a little bit further. I think these are the most difficult ones, so that's why I've chosen them for this lecture. And the first one is the multicollinearity, and the second one is the linearity. So we'll look at those each. So, to adhere to the multicollinearity assumption, there must not be too high of a relationship between the predictive variables. And the illustration, the image here, I think clearly illustrates this point. Who stole my fish? says the penguin, and he wants to know which penguin stole his fish. And of course, that is a very hard job to determine. And what the reference is that if you have a predicted value, if all your predictor variable are very highly related, you can exchange one for the other. So adding another predictor variable doesn't add a lot of explained variance to the models because they're interchangeable. They do the same thing. So if that is the case, then you could run your multiple regression with all of these predictor variables, but they all do the same. So it's superfluous in that sense. And you should, well, there are a few things. Of course, if they are essentially the same, then it wouldn't matter if you take one out. So you could limit your amount of predictor variables that you then put in there. And there are also some options to use some principal component analysis, but we will not go into this in this course. But you could use a principal component analysis to get one component based on all these predictor values, so you still have one which is indicative for all the others. So there are a few options. But first, of course, we need to determine if this is the case, if we have any multicollinearity in our between our predictors. And of course, you could look at the correlations between your predictors. And we've seen with the correlation that you get high correlations if you have observations in the along the diagonal, so the top right corner or the bottom left corner or vice versa, and your correlation goes up if you have observations in there. So we've played the guess the correlation game last week, and we've seen that it's quite hard to even based on the scatter plot to predict what the correlation is that is associated. And the other way around, it's of course also quite hard if you only have the correlation value to imagine a visual scatter plot based on that correlation. So looking at the correlations is one thing. It's a good start, but also creating a scatter plot on all the relations, all the possibilities between each predictor. So if you have two, of course, then there's only one scatter plot for the two predictors, but you could have more, and then you want to look at each and every one of them. So you can create a matrix scatter plot in SPSS, which essentially makes the entire scatter plot, makes multiple scatter plots for all the combinations that are possible. There are also a few indicative diagnostic values that are calculated within SPSS, which Field also explains. We could have a VIF value, so in one of the outputs in SPSS, the VIF value is told, which is essentially an aggregated indicator of the amount of relation between these variables. So it maxes out at 10, and if the assumption holds, then your mean VIF value for all the predictors needs to be smaller than 1. So that's an indication to look at. And the other one is the tolerance, which is also provided by SPSS, and this should be higher than 0.2. So these are not significant tests. These are more like thresholds that you can look at to see to determine your conclusion. But I think that the most important thing is just have a visual look at the data, because it gives you an indication if there's a linear relation. Linear relations, if that is there, you see it, right? You see the dots that are on a line or not. So always try to inspect your data visually. That helps a lot. So this is multicollinearity. Is this clear?
Yes. Yeah, can I ask something about this?
Sure.
So you said that we could also make like a matrix scatter plot and look at the relations between two predictor variables. But it says that it must not be too high. So what would be too high? Like, is there a...
Yeah. So there isn't a definite cutoff, right? So the combination between doing the correlation and looking at the scatter plots. So let's, for example, you looked at the scatter plot and you see that there's somewhat of a linear relation, but you're not sure how if it's too high. So you could then also afterward look at the correlation. So what are the actual correlation values? And then determine based on that if you deem it too high. But again, there are not clear cutoff points based on the correlations and the scatter plot. So even within the correlations, of course, you could say, well, if it is a significant correlation, then I would deem it a problem. But as we've seen, if you have a lot of participants, the significance of a correlation could be, well, even with just a correlation of 0.3. So even the significance of the correlation is not an indicator. So if it's on the brink that you're not sure, you could use the tolerance values and the VIF values to make a final decision. So I think that order would be good. Does that make sense?
Yeah, it does. Thank you.
Okay, you're welcome. Very good.
I have a question.
Oh, sorry, I muted you. Go ahead.
Yeah, in field it also states that you can check the eigenvalue and in combination with the variance proportions. Is this also true?
It's absolutely true, but in explaining this, I would need to explain how you do principal component analysis and what eigenvalues actually are. So those are indicators that you also could look at, but the interpretation of such results are a little bit harder. So.
All right, thank you.
Yeah. Okay. So those are the multicollinearity. The next one, linearity, is essentially you're looking at the relations again, but this time between your predictors and the outcome. So for the linearity assumption to hold, the predictor must not have a linear relation. So the predictor must have a linear relation with the outcome variable. And this is, of course, logical in the sense that we're doing linear regressions. So what that means is the regression model that we fit creates a line. It creates it based on the regression model that I've shown you, where you predict y based on the intercept and the slope. It determines a linear line, and then it sees how much do the data points actually differ from this line. So if there is no linear relationship between the predictor variable and the outcome model, for example, you have a parabola, or it's more it goes up at one side, or it could have any other shape. If that's the relationship that there is between the predictor model and the outcome variable, then you shouldn't fit a linear model, because then you will have a line based on a parabola. That's not logical. You shouldn't do that, right? So in those cases, you should deviate from linear regression, and you should go to other kinds of regression. So maybe log linear regression, or maybe logistic regression. So there are other options. But of course, if you are looking at linear regression, then this assumption, of course, should hold. There should be a linear relation. So that means, again, that if that is the case, you have to look at each predictor variable, how that relates to the outcome variable. So here again, you could look at the correlations and you could look at the matrix scatter plot between those two. Is that clear?
Yes.
Good.
Can I ask a question?
Sure.
If we look at correlations, for example, at which value should we assume that? Well,
it's the same point as the previous question. There are no clear cutoff points, but so if you look at your data, and if so, your correlation goes up if your data points are closer together, right? So if you have a value on your predicted value and the relation between the outcome variable is well, every dot is on this line, then you have a very high predictive model. But even if it's more spread out, you could see that it's a linear relation. As for if the dots are like this, are like a parabola, you see that, then you clearly see that there's not a linear relation. So in terms of what the height of the correlation is, again, it's you can't really determine. But because even if you have data points that are in a parabola, you will still get a correlation value if you calculate the Pearson's correlation. So it is always good to first look at your data to see what it's look like, so
it's better to always plot a graph.
Always.
Okay, thank you so much.
Yeah. Okay. Very good. So very good questions, and of course, because with a lot of the statistics that we do, we have a clear decision rule, right? If you use the significance testing, the Neyman Pearson paradigm, we have at least a clear decision scheme on where we decide one thing over the other. But for a lot of these assumptions, there isn't such a clear-cut decision rule. So yeah, it's a bit arbitrary. But well, if there clearly isn't a linear relation, then you see it. You see what it looks like in that sense. Okay. So we're going to do an example, and we're going to just build upon the example of last week, where we predict study outcome based on IQ, but we're also going to add motivation. So this is the theme, right, that we started back a few months ago in September, where I asked you to look in the eyes of your neighbor on Zoom and do an estimate of their intelligence. And we talked about what kind of things make that you have a certain prediction on the intelligence of your neighbor, of your Zoom neighbor, and that is one, of course, that you could be very careful and just say, well, I expect you to have the average of the intelligence. But then there were some students that said, well, maybe I estimated the intelligence of the one next to me because I know him or her, and I know she's very motivated or has a very high scores within their study. So motivation. So in that sense, if you think about variables that can predict and it's operationalized, and you can operationalize that in scores on a test, motivation test or IQ tests, or even the grades, the average grades, for example, that one has for the study, then you can model this in a linear regression model. So this is what I'm gonna do. So we're going to try to predict the study outcome based on the intelligence and the motivation. And for this, I'm going to let's first do it in SPSS. So let's go there. Let's see. I have IQ. I have a study outcome, and I have the motivation as three variables.
We can't see the slide.
Oh, sorry. Yeah. So I switch to SPSS. I have these three variables here, and we're going to perform the regression analysis, the multiple regression analysis. And again, I'm going to ask you, where do I need to go? So guide me.
Analyze,
Yeah.
then regression,
Where do we have that?
like 6 down.
Yeah, 1, 2, oh, there. So I'll zoom in. We're here, and we have the general linear models, and we have the regressions over here. And so I told you that sometimes it doesn't. If you don't have a linear relation between your predictors and your outcome variable, you should go for other kinds of regression analysis. And so you see here you have also curve estimates or partially. There are other options than we provide in this course. So these are topics that can come along the way when you further in your studies. So the one that we are going to be looking at is the linear regression. So this is the one we're going to do. So now what? We want to predict study outcome based on motivation and intelligence.
Put study outcome in the dependent variable, motivation and IQ in the independent variable box.
Okay. So you're saying this one, motivation, no, sorry, not motivation, studieprestatie, dus study outcome, and motivation and intelligence in the independent box. So does anyone have an idea of what this box is? Because we have block 1 and we have a next button and we have an enter thingy.
It's your regression model.
Yeah, it is your regression model, but I have a next thing here, and then it goes somewhere else and it disappears, and I can go back and there it is again. So what is happening here?
I think you can compare different models against each other.
Yeah, exactly. But not just different models. It's so what this box means is that you can add to your model. So, for example, last week we looked at the prediction of with only one predictive variable. So what you could do here, and this is what this box does, is it offers you the opportunity to run a few regression analysis where you actually expand the model, add predictive variables, and to test if your new model where you added a new variable adds something to the explanation of the variance. So maybe there is some theory that is well established, but you as a researcher think well, in this theory it is hypothesized that we have these variables, but I think that this variable also has plays a very important role. Then you could run this analysis with the original predictors of the theory, and then add your new one to see if your new one adds something to the equation in that sense. So if you would want to do this, you could say, well, I predict study outcome by IQ, and in the next block I will put motivation. And what this will result in is the results of two regression analysis in SPSS, where SPSS does the first one only with IQ and the second one with IQ and motivation. And it tells you how much explained variance both models have, and it also tells you what the difference is between those models. So if there's only a 10% increase in explained motivation, is that a significant increase in explained variance? So it also tests statistically if the added value is relevant or not. So this is what you can do in these blocks, and we're going to look at these the outcomes. here.
And I'm sorry, in this test, if we do this, we also have the Darby-Watson test. That is one of the assumptions that I couldn't understand from Field's book. This assumption applied in this situation when you already have a predictive factor that you know that it is well known, and you try other factors, and you also need to test for that assumption.
Yeah. So one of the things that can go wrong here is that you just keep on trying and trying and trying and trying, just like the chance capitalization, right? So you have to be very clear if that is if it's a search goal, right? Then you should state that clearly in your research paper. As for the specific assumptions, I haven't highlighted this specific assumption, so. Make sure that you firmly understand the ones that I've discussed in this lecture for the main part, right? Is that okay?
Yeah, thank you.
Okay, you're welcome. So we have some options, some statistics, of course. And if you look at these statistics, then what do we have here? Of course, we have our coefficients, we have the model fit, and we have this one, the R squared change. And this R squared change refers to the fact that if I now add a new predictive variable, I want to see the change in explained variance. And by ticking this one, SPSS will provide that information. Will test if the change in explained variance is significant or not. Of course, we would like to see some descriptive statistics, and we like to see some diagnostics in our tests. So we'll go for this one. We'll skip the plots for now. The save options, we don't usually we don't need the save options for the for interpreting the results, but there are a few that will make sense. So for example, the predicted value unstandardized means that if you run this, then SPSS will create a new column in SPSS with the unstandardized predictive value. So you don't really need it, but if you add this one, you can see for each individual what is predicted for this person and what is his actual score. So in that case, it can be useful sometimes to see, to look at what your model is predicting for your individuals. But the most important parts here are the Mahalanobis distance, the Cook's distance, and the leverage, because those are the diagnostics values that can help you find the outliers, right? So we talked about this last week. SPSS also gives you these diagnostics overview to see if, for example, what is the lowest Mahalanobis value, and if the lowest Mahalanobis, what is the highest Mahalanobis value of the Cook distance or the leverage, and if even the highest of these values is lower than your threshold, which is indicated in field, then there isn't anything to worry, right? So if you say the Mahalanobis value must not be higher than 15, and you see within the diagnostics output that the highest Mahalanobis value in your dataset is only 11, well, then there's no problem. You're okay. But if it states that the highest value that you have in your dataset is higher than 15, for example 18, then you have to look at your data and find this person to take the person out. So by adding the Mahalanobis Cook distance and the leverage values to your dataset, if you have an outlier, you can easily find them by looking at the column, finding the value, and then you know who it is. So this is useful information to add to your not the outputs, because everything that is under save means it will create a new column in your data set. But it's useful to add. Do we have some options here? Well, this is okay.
I have a question.
Of course, go ahead.
Because you just said, let's skip the plots, but don't you need the plots
yeah,
to
you're
test
right.
for homoscedasticity?
Yeah, that's a good point. Very good, very good. So we need the plot for homoscedasticity. So we need the Z predicted value and the Z residual. So the Z stands for standardized. Very good. Thanks for reminding me. Well, yeah, that's it. Let's do this one.
I have another question.
Go ahead.
For the R-squared change, shouldn't we have 2 blocks so you can compare between 2 of them?
Yeah. Oh, I didn't put it in. So this is why I need your help, right? Put IQ. So which one do you want in the first block? First IQ and then motivation, right? So because we looked already at IQ and then this one. Okay. Do I have everything now? Because now I'm not sure.
Yeah, I'm not even sure.
Anyone else?
Now I have like 3 blocks. It says 3 out of 3, so I think you have.
Oh, I have one. I want to this one to. Okay, yeah.
Shouldn't there be
no,
a combination of both?
No, there should not be a combination of both. So, oh, I'm really botching up. So now I have 1. In the next one, I will add this one, and now I'm done. I don't have anything here. No, great. Yeah.
I'm confused about.
Someone said I'm confused about. Go ahead.
Yeah, I don't understand. So you've put the dependent versus motivation as one block, and then versus IQ as another block, and then what's the last block?
No, that should be it. So I'm looking at it also, and I'm seeing that I have 1 here and 1 in the second, but I see that SPSS is not telling me anymore that it's which one of the blocks it is. So I'll try to reset.
So you should. You should put.
I'm starting over. Let's see. Doing it again. Regression.
Sharon, I think this is a glitch in the SPSS thing because it did it in the homework as well.
Oh, really? Okay. So this I'm running the latest version of SPSS. So maybe that is related. It still says 1. Okay, now don't make any mistakes. I've got study outcome here. IQ add 1 block. I add a new block. I add motivation.
And it hasn't changed.
Okay. Okay, so it's just not updating the field here. We'll run the analysis to see what happens. So I'm gonna do the statistics again. R-squared changed, descriptives.
Sorry, I have a question. What if we have 3 predictor variables? Then do we add 3 blocks?
It depends on what you want to test. So as I stated, if there's a dominant theory which has a few predictor variables, and you only want to know if your added one is relevant, then you put all the known predictors in one block, and you add your added predictor in the next block. So it depends a bit on what you want to test.
Oh, okay.
Yeah.
Thank you.
Let's see. This was okay.
Sorry, but why don't you look again at the interaction between the 2 in one block?
Oh, that's an interesting point, because that is not what we're doing with multiple regression. So with the multiple regression, we want to know what the influences is on one predictor if we keep the other constant. So by not adding an interaction term, you're not allowing your model to have different predictive slopes at different values of the other predictor. But I'll go into this later in this lecture. I'll come back to that.
Okay, thank you.
If you do add interaction, it will mean that we're not, it will mean that we're doing moderation analysis, which we'll also cover next week. Okay, let's do this. Let's see if it actually performs the different kinds of... Yeah, it does. So what we have here, of course, is some descriptive statistics. We asked for some correlation, so we're looking at the collinearity and the linearity diagnosis. So that means study outcome is our predictive value. So if we want to know if there's a linear relation between the predictors and the outcome variable, then we need to see high correlations and a linear relation between IQ, motivation, of those two with study outcome. And well, this is 0.8 and this is 0.7, so it seems fairly high, and we'll try to make a scatter plot in a few minutes too. But the assumption of multicollinearity, I think it's broken. We're not. We have a problem here, right? Because motivation and IQ are correlated 0.97. So this seems way too high to for this assumption to hold. So based on the correlation, I am suspicious here, and I think if we look at the scatter plot, so let's do one. There is one option here on the legacy dialogues to have to create a scatter dot matrix here, where you can say that you want a matrix scatter plot. So there you can do this through the, I think you can do this through the chart builder also, but this one gives also a neat overview of those variables. You can just put in the variables that you're interested in, and it will create those scatter plots for you.
Sorry, I missed how you did that.
Yeah. I went to graphs, legacy dialogues, and I chose scatter plots.
Okay, thank you.
And well, you see, well, the assumption of linearity is met, right? You can eyeball this because there is a linear relation between study outcome, this study outcome, and IQ. This looks very linear, and that also holds for study outcome and motivation. That also looks very linear. But there's also a very linear relation between motivation and IQ. So we have a violation of our assumption here, of the assumption of multicollinearity.
That's a question.
Go ahead.
Why, if you go to the matrix, why is IQ and motivation, it's 2 times in the matrix, right? Why is it not identical?
Why isn't...
So the middle down and the middle right, they're supposed to be the same, right?
This one?
Or no? Yeah.
It's mirrored, I think.
It's mirrored, right? Yeah. So it's flipped like that. But this one.
Oh.
Yeah. So
okay.
So I'm only looking at these 3 because this is the same, but then flip the other on its flipped on its vertical axis. So you you see this bit here, it's the same as this one. So these are the same. Yeah? Okay.
Yes, thank you.
So I'm gonna go through and start interpreting some results, and we've done 2 models, so we can see that we will look at what the added value is, but keeping in mind that we have a violation of our assumption, so we should be wary in how to proceed at the end. But so we have the correlation. and this is the main table where we find our results. So it's the model summaries where we have model 1 and model 2. So what is model 1? What predictors are in model 1?
IQ.
And what predictors are in model 2?
Motivation.
And IQ and motivation.
IQ and motivation, yes. So the blocks mean that it adds the new variable to the first one. So indeed, the second model contains both IQ and motivation. So the amount of explained variance of only IQ is the correlation between the model and the outcome is this 0.83, and the amount of explained variance, so we square that correlation, is 70%. And if I add motivation and have them both in the model, so motivation and IQ, I can explain 75% of the variance, and the correlation is 0.868. So,
can I ask something? Sorry.
Sure, go ahead.
I'm confused because I thought you said we had to put them in separately. But
yeah, so in the blocks you put them in separately. So you start with block 1, you put in IQ, and you go to block 2 and you put in motivation. But the way SPSS processes this is that it adds everything that is put in next block to the previous blocks. So I have IQ put in block 1 and motivation in block 2. So model 1 only contains IQ, and model 2, which is not block, it's a model. Model 2 contains both.
Okay, thanks.
Yeah? Very good. Well, I see that there's more variance explained by the one where I have both in there. So if I want to know if that is a significant change, then I can look at the difference. I can look at the difference between the 70% here and the 75% here, and that is 0.051 in explained variance, so about 5%. And the question then is that a significant added value? So to get to that point, we test with an f-test this value, and it returns that we get a significance of 0.01, which is lower than 0.05. So it actually states here that adding this variable, it's significant contributor to the raising of the amount of explained variance. So in terms of which model has more predictive value, then it's the second model which explains more variance. Of course, if we want to be strict, then well, we've determined that we have one of those that the two predictor variables have a very high correlation, so we have a violation of assumptions. But if that wouldn't be the case and this would be the outcome, then you could certainly argue that you would be better off with adding this predictor to your model. You had a question. Go ahead.
So the first significant F change will always be 0 of the two because you don't compare anything.
Yeah,
so
of course. Yeah, sure. Yeah.
Okay,
yeah.
You.
So you're talking about this line.
Yeah.
This is always 0. Yeah, because it's not. Yeah.
Okay, thank you.
You're welcome. Was there another question? No. Okay. So this is the most important table. We'll dive into the rest of them, but I indeed need coffee at this moment. Getting a dry throat, so we're gonna take a break. I'll see you in 10 minutes, and then we'll continue. Is that okay?
Yep.
Everybody up for coffee? Let's go. See you.
Hero?
question.
Short.
Sorry, just one question. Did you say how did you know which model was more predictive?
I'll get back to that when I get back into the break. Yeah.
Thank you.
You're welcome. So, we're continuing with coffee this time. So, nice, warm, fresh cup of coffee. Ready to go. So just before the break, there was a question about, again, where do we see the which model explains more variance? So it's here. You see the R square, which indicates the amount of explained variance. It's the squared correlation. Here it's 70%, here it's 75%. And then that raises the question, is that 5-ish% that we have more, is that significant? And we find that difference here, that 5%, and this is tested with an F-test. And we conclude based on this result. So that's where we find this. Does that answer your question?
Yes, that's super clear. Thank you.
Very good.
Sharon, can I maybe ask another quick question?
Go ahead.
The homoscedasticity assumption, how much of a variance would be too high for that? Is there like a threshold, or is it just an indication?
No, it's just an indication.
So
again, it's just eyeballing.
Okay.
You don't have a clear cutoff point. There are no tests to determine this, so it's just looking at. So, but yeah.
Okay.
It's when it's really off, you will see it in the sense, and I think in the weekly assignments or in the tutorials we will cover a few of those scenarios where it's really off, and field also covers a few of these. And then you will clearly see a funnel or different kinds of shapes of variance. So I wouldn't be too concerned if you don't really see the difference between like this kind of spread versus this kind of spread. Those are generally in the same line, but if you really see different shapes coming up there, that's a clear indication that we have a problem.
Okay,
yeah?
Thank you.
You're welcome. Now the next plot we have here is essentially an ANOVA results. But what it shows here for the two model is how much variance is explained in terms of an ANOVA. So if you think of variance, you well, we've discussed this, right? That the total amount of variance is just the sum of all the deviations of each individual scores to the mean of the entire group. So you can determine the in advance or based on your data set the total amount of variation that there is. So if you have a total amount and you have a part that is explained and the part that is not explained, then the explained parts and the total parts are a ratio, right? So a percentage. If you have 80% from 100, 80 from 100, then we have 80% explained variance. But these are the same variance components as we've been using in ANOVA. So if I put these back, this is the total amount of variance, this is the explained part, and this is the unexplained part. I can also take the unexplained part and the explained part, get a ratio, what is the signal to the noise ratio, and then I have my F value. And that is what is shown in this plot, in this table here for both models. It's determining the amount of signal to noise ratio for model 1 and for model 2 to determine if this is significant. In other words, do we have as this entire model, does it explain a significant amount of variation? So it's essentially doing the same trick as we've seen with the previous ANOVA. It's looking at the signal to noise ratio of your entire regression model. Does that make sense?
Can I ask a question?
Yeah, sure.
What an F of 87.007, would that then be an explained variance of 87%?
No, because the F value is about the relation of explained variance to unexplained variance. So it's a signal to noise ratio, whereas with the explaining variance, you take out the noise part
and
you use the total. So that makes it a percentage that can really be expressed as being between 1 and being between 0 and 100%, because you're comparing what is explained to what is possible.
Okay, right.
Yeah.
Thank you.
Sure. Very good.
Can I also ask a question?
Yeah.
There in the SPSS slides, you see the two F values, and the first one is higher than the second one, but wouldn't it be more logical that in the second one there was more explained variance, so the signal to noise would be higher?
I'm
not sure, but it just seems... How could there be more signal in the first one?
It's not being that there's being more signal. Well, there actually is a bit more signal, but it's the ratio, right? It's the ratio between, here you have the sums of squares of the regression. So this is the explained part, the sums of squares of the explained part, and this is the unexplained part. So it's the standardized proportion of these two. And you see that in the second model you have a bit higher explained sums of squares compared to this one, but you see that the residual is here a bit higher and here a bit lower.
Yeah. But how could the F value then be lower than in the first one?
You have to divide by the degrees of freedom, and so here you have your degrees of freedom for the first model, because it only has one predictor, and in the second one you have 2 degrees of freedom because it has 2 predictors, and that impacts the mean squares, because the mean squares was this divided by that is still the same, and here it's the sums of squares divided by the degrees of freedom, which reduces your mean squares significantly. You see?
Okay.
So that will make the F value smaller. So I understand your reasoning, and then the explanation is the fact that when you add more predictor variables, you also add more degrees of freedom to your model.
Okay, thank you.
Yeah, good questions.
Does that
yeah, go ahead.
Does that mean, so for the first model it has a higher F, so would you then say there's more explained variance in the first model? No, because it has a higher F than the second one.
No, it's not because it has a higher F. The F again is not the proportion of explained variance. The F is the signal to noise ratio. So what you would say here, in the first model, there's a higher signal to noise ratio than in the second model.
But the second model still explains more.
Yeah, because if you only if you look at the percentage of explained variance to the total variance that there is, so that's above that percentage here. That's 70% versus 75%. So yeah, it's more explained variance, but there's more, but there's less there's less signal to noise. So. And that also ties into the fact that we have a lot of multicollinearity, that are both variables are doing the same thing, and therefore will influence the if you combine them, the amount of signal to noise ratio. So we won't go into how exactly this happens, but this is something that results in. So it also tells you, of course, then that only looking at the fact that this percentage of explained is more than that, and that difference is significant, it doesn't mean that it gives you a better model. It because this signal to noise ratio is much higher than that one. So you have to tie in these factors to determine which one is the best. Yeah. Okay, so we go after this into some of the diagnostics.
Could I ask a quick question?
Yeah, go ahead.
The second model, would it because it's IQ and motivation, would that be like at the beginning if you put both of them in the same block?
Yeah, so if you put both of them in the same block and you use only one block, you would get an explained variance of this one. So this would be exactly the same for if you put everything in one block. But
and do you always separate the variables between blocks?
As I stated, only if you are interested to see what your added what your new predictor variable adds to the total. So if from the get-go my goal is to just know if IQ and motivation are predictors for study outcome, then I can put it in one block. I'm done. But if I want to know if for example, if it's well established that IQ is a good predictor of study outcome, and I want to know if motivation plays a factor in this and is an added value to the model, then I can put it in separately and get an estimate of how much extra variance there is to explain. So the choice is yours as a researcher, but in terms of if you want to write a research paper on this and the goal is just to combine these two, you would write it differently than if your goal is to tell the world my variable that I thought of is of significant value to add to the established model for that, for example.
All right. Yeah. Okay.
Yeah. Good.
Thank you.
You're welcome. So we have some collinearities. The VIF values that we've talked about in the slides are shown here. So we can look at those to determine if we have violations of assumptions. And let's see. Let's look for a second at the diagnostics, because if we want to determine if there are
could I just ask about the VIF? Wouldn't these be too high?
Yeah, sure, absolutely. And that's what we concluded, right? About we've seen in this example that we have a problem with our data because our two independent variables are related way too high.
Yeah.
So
okay,
it's absolutely a problem. If you look at these VIF values, then yeah, good observation. So let's look at the diagnostics for a second, then we'll dive back into the slide. So what we have here is some descriptive statistics on the diagnostics. So we see the minimum, the maximum, the mean, standard deviation, etc. And what we find, and the things that are most of interest to us, are the Mahalanobis values, the Cook's distance, and the leverage. And those are the three diagnostics that we also wanted to see in our data set. So if you look up fields, then especially for, I think the Cook's distance, it needs to be lower than a certain threshold. I think it's 2, but I'm not sure by heart. For the Mahalanobis distance, it depends on the sample size. So for you don't have to know these values by heart, so just look it up in field what the threshold is. But if these maximum values for these 3 are higher than the maximum values of the 3 are higher than the thresholds, then you need to go into the data set and look up who the person is that has this higher value. So when we ran our analysis, the regression analysis, we asked to save the Cook's distance and the Mahalanobis and the leverage in our data set. And if I go to our data set, that meant that we added a few columns. And these are the columns for the Mahalanobis, for the Cook's distance, and for the leverage. And that maximum value of 7 for the Cook distance, we can find this one in our data because we added the columns of interest. So if we look at this, I think SPIS has crashed. Let's see if I'm still able to go to the outputs. No, the data. Yeah, here it is. This one is the 7. So by looking at the diagnostic information and determining based on the threshold if there is a problem, I can go into my data set, find out which person causes the problem. So it's this one, and then I can take measures and take this one out of the data set, or if maybe there are more because it only shows the highest, right? So I could also
Was
run.
that 7.3?
Sorry?
I thought it was 7.3.
Oh, it could be, yeah.
Oh,
So
yeah.
I could use a filter to find everything higher than 7.3, or I could look it up in some diagnostics on this one. So we have 7.3. You're right. Here it is. And I think for this sample size 7 is okay, but again I'm not sure. We have to look at the field what it says for the sample size. The question: what is the filter?
The person.
Sorry.
What happens then if we found it and then we know who's causing the problem, basically?
We take it out of the data set.
Okay, so we can just take it out and run it
Of
again.
course you report it in your paper. So we found one outlier with a Mahalanobis value higher than the thresholds, and we took this person out for our further analysis. Yeah.
Okay.
So as long as you're clear on what you're doing, and that was the whole point with EJ and Danny in the base debate, right, over our good practice. As long as you're clear on what you're doing and don't cover up, then it's okay. So just report it and then you're done. I see a question in the chat on what filters I'm talking about. We've covered this in the beginning of the course. So if I want to find something, I can select cases, and for example, then I could select. Oh, this is out of frame. Let's see. SPSS, yeah. And for example, I could use the Mahalanobis as a search field, and I could say only select cases where the Mahalanobis value is higher than a certain threshold. So you can use the things that we used before in selecting participants to select your cases essentially. So yeah.
So would it be possible to spot this person in like a scatter plot or something?
Yeah, probably. But it depends. If it's really a big outlier, you would see it right away. So, for example, the scatter plot that I showed you last week, where I plotted, I had this outlier which was totally in the extreme on one end and low at the other. Then you can see it. But sometimes, if you use these Mahalanobis and Cook's distance, they could be a bit closer. So it's a bit hard to determine if one is really an outlier or not. So you have to go on the results of the Mahalanobis.
Right, thanks.
Yeah.
So do we run the test again after filtering out?
Yeah, exactly. Yeah, absolutely.
And how is the threshold set for the Mahalanobis?
It's the field provides a few guidelines, and it's based on the combination of sample size. So I don't know it by heart because it's not just one value. It's if it's higher than 100 people, then it should be this, and if it's lower than this, then it should be that. So look it up in field to find what the threshold is. That's your question, right?
Yes, indeed. Thanks.
Okay. Very good. Okay, so we're going back to our slides. We were in the example. So looking at our data, am I missing some? I'm missing something. Wait a minute. I'm gonna go back to SPSS for a second. Yeah. Output. Yeah, sorry. This one. We have to look at this for a sec. Because, so we've determined that we have a significant predictor. We have determined that we have some problems. We have to choose a model. What model would you choose? The first or the second at this point?
The second.
Who agrees? The second?
If the assumption weren't violated.
Yeah, okay, exactly. So because the assumption was now violated, I think it would be better to go for the first first one. But maybe we could even run the same analysis and run it only on motivation to see if to separate those two. So there are all kinds of possibilities. But let's say we choose the first one. Okay, let's choose the second one, because if I choose the first one, we'll be stuck with a simple regression, and we won't have the multiple regression. So I'm going to look at the beta coefficients for the second model, just to get it into the framework of what we need to interpret in terms of our regression coefficients that we have. So you've seen the regression model in our slides, and we were talking about the intercept, the constant, and we were talking about the slopes for the two predictive predictor variables, IQ and motivation. So within the coefficients table, we get the unstandardized coefficients. So these are the betas that I've shown in the slide. So we have a constant of -30. Well, this is not really relevant because it's the place where, if you have all axes on x values on 0, where it hits the y-axis, and these are interesting. So we see that for IQ, we have a beta coefficient slope of 0.2, and for motivation we have a slope of -0.6. So this means, this is strange, right? Because we see that the higher your IQ, the higher your study outcome, but the higher your motivation, the lower the study outcome. So there's definitely something wrong with this motivation as a predictor. Of course, this is all simulated data, so don't worry. This is not saying anything about real life. But here we see the weights, the slopes of the individual predictor variables. We also get the standard error of this, and if we have the beta and the standard error, that means that we can calculate a t-value and test if our t-value is significant. So for IQ, we have a significant t-value. It's lower than 0.5. And for motivation, we also have a significant t-value of 0.01. So this gives you an indication, and sometimes a predictor does not, in the totality of your model, a predictor might not be significant, which will indicate that you should not take that predictor into consideration because it's not a significant value to your model. So there are a few ways. Of course, we predicted. We knew this already because we've used the blocks, right? And we've seen that by adding this variable, we have added explained variable variance. But what we see here is what is the significance of the beta coefficient on its own. Yeah. So
this B is the slope.
Yeah, this is the slope of the, and we'll look into that slope in a second. What this means and what it looks like. I see the question in the in the chat. We're now looking at the second model just for the sake of this lecture to go into the multiple regression. But we have to keep in mind that we have a violation of assumption. So in reality, if you would do this analysis, you would have to stop because of the violations of assumptions. Okay, back to the slides now. So we have IQ, motivation, and study outcome. We're going to do the regression analysis in R for a second, which will get us our intercepts, which we already looked at. We have the beta coefficient for the IQ, and we have the beta coefficient for motivation. These are the same as we've seen in SPSS, right? Minus 30 plus 0.26 and minus 0.6. This is the same as we have in our SPSS output. This, and this. So what I'm doing now is I'm applying this regression, the beta coefficients to our beta to the value. So we had B0, and in one of the previous slides I used the Greek letters. Now these are estimates of our actual population parameters. So I used the small b's. 0, 1, and 2. So we can now apply this to the regression model. But what I want to do is try to visualize this. So this B1 and B2 are the regression slopes of the regression analysis, which tries to find an optimal fit of the regression plane in this case, because we've been talking about regression up until now always about one line, but because now we have two predictor variables, we can create a regression plane because we have a study outcome which we want to predict based on IQ here and motivation. So this is motivation, the high, low motivation, high motivation, and we have IQ going up in that direction, and we have the study prediction, the study outcome going up on the z-axis. So what you see here is the red dots are the data points, and the green plane is the regression plane. So, and there's something a bit wrong with my interface. So if if I move it, it doesn't really go as expected. But you have this interactive plot also available in your in the handout. So what we see here from this side is that the regression plane, this line, this is the slope for the relation between IQ and study outcome. So we see this was 0.26. It's this slope is this line, and it indicates that the higher the IQ, the higher the study outcome. And if we look at the other direction, oh, this is so hard. Yeah. If we look at the other direction here, you see that we see the relation between motivation and study outcome, and the slope again here was negative. It was a negative 0.6. So we see that the higher the motivation, the lower the study outcome is. And what we also see is that, and that is coming back to one of the earlier questions on why don't you add an interaction, because we're not doing an interaction or adding an interaction, because we're not doing a moderation analysis, that means that the regression plane that is fitted creates a plane that is leveled out for every predictor. So that means that the relation of, for example, the relation between intelligence and study outcome. Let's go here. The relation between intelligence going up to the right and study outcome going up. This slope, this 0.26, this slope is the same at every level. Can you see this? So do you see this line?
Yeah.
And can you see this line?
Yes.
And do you see that this line means that it's on a higher score of motivation? So the motivation is going down in this direction here. So for every level of motivation that you have, the relation between IQ and study outcome is the same. So what you're essentially saying with performing a multiple regression without such an interaction term added to your model is that you want to know the relation between one predictor variable controlling for the other variable. Do you see that?
So it's like an ANCOVA.
It's exactly like an ANCOVA. And the ANCOVA does the same thing as here, but one of those predictor variables is a categorical predictor variable. But in essence, it's the same thing. It states, I want to know what the predictive value of this predictor is, keeping the other constant. And that is what a multiple regression allows you to do. So we see here that for every level of motivation, we see that the relation of IQ with study outcome is the same. So all lines are just have the same slope. And what we'll see when we go into moderation analysis is that because in moderation analysis we do allow an interaction, that we can have a difference, and we'll look at this next week. So this plot gives you an overview. Again, iterating, the red dots are the actual data points. The green plane is the regression plane, and I've just added these blue planes to make the slopes more visible. Is this clear? Does this help?
Yes.
Very good. So in this looking at this plot, can you point to me? Can you point me to the unexplained variance? if I'd asked you from point, you see this plot, what is the unexplained variance here?
The distance between the red dots and the green thing?
Yeah, exactly. The distance between the red dots and the green plane. So if this is the green plane, well, it's not, you see the green plane, the distance between that green plane, the expected outcome, and the actual outcome, the actual score of the individual, that is the unexplained part. So you see that we have all these dots very close to our expected outcome, our model. So that is the unexplained part. Very good. And for example, the explained part, what would that be? I'm trying to zoom out again and make it straight, but that's hard to do. What would be the unexplained part? Sorry, the explained part. The distance between what?
The dots and the blue planes?
The dots and the blue planes? No, the blue planes are only there to visualize the lines. So we only have the regression plane in green, and we have the red dots. So what would be the explained part of the variance if you look at this?
Maybe the difference between the red dots and the like the black line that goes between the red thing. I hope you understand what I mean. Yeah, like a line between the red dots. I think that like the average, I guess, or like the line, and then the difference between those two.
Yes, so it's not really the case, but you did mention the average. Why did you mention the average, and which average are you talking about?
I have no idea.
Someone else can chip in, of course.
The average of the data points, like the observed values, and then their average of this group, and then that to the green thing.
Yes, yeah, absolutely. So when we're talking about explaining variance, we're talking about explaining variance of the dependent variable of the thing we try to measure. And the thing we try to measure here is study outcome. So the average of our outcome variable, the average of study outcome, is what is the thing we want to know. We want to know what part of the variance of the individual scores is explained by the model. So if we want to know the explained part, we would have to look at the difference indeed of the average of study outcome, which is, I don't know, maybe somewhere here, the average of study outcome and the green plane. So that distance we need to look at the explained part. So we are again looking at what is there to explain? Well, there's variance. Variance is related to the distance of the average to the actual data points, and we can decompose that total variance into an explained part. In this case, it's the green regression plane is the thing that we have explained, and as we correctly concluded earlier, the distance from the green part to the actual dots is the thing that is unexplained. So that's a very good observation. So what are the expected values? Well, we just have to fill in the regression equation. So if we know what B0 is, if we know what B1 is, and we know what B2 is, we can just fill in those values and then see what the expected study outcome is based on a known IQ and a known motivation. So we can just apply it. So if B0 was minus 30 and B1 was 0.2, well, it was 6 and a bit, but this is rounded. We have some Q score for the first person in our data set. We have the weight of the beta coefficient for motivation, which was minus 0.6. And we have the actual motivation score. This means that we can calculate what the expected study outcome is for each and every individual. So we're just plugging these numbers. So we add the multiplication of these two, and we add the multiplication of these two, the last one, and of course we add the intercept, and that gives us an expected study outcome value. And that is how you apply such a regression model. And you can imagine that if you have a regression model that is good, that has a high predictive value, and that is robust, for example, over time, so you've done a few replications and you always get to the same beta coefficients, then you can use such a regression model in real life. So even for data that you haven't seen, you can use your regression model, calculate someone's IQ, calculate someone's motivation, and then you have an indication of what study outcome could be. So you could, if you have a valid regression model, then you could actually use it in real life. So how far are we off? In other words, what is the error that we have? So we have our actual study outcome for each individual. We have our predicted study outcome, and the difference between those two is the amount of error that we have in our model. And this means that for each individual, we can calculate how much we're off based on the difference between the actual outcome and the model. If we, as a question to you, if we correlate the model and the study outcome, so if we just take these two variables and correlate them, what do we get then?
Could you repeat that question, please?
What do we get if we correlate the model? So all these numbers, correlate the model with the study outcome.
See how well the model fits?
Exactly. And that value, the correlation between this one and that one, or in terms of SPSS, the correlation between my actual study outcome and my predicted study outcome, this correlation between these two columns is exactly what is given here. This R means it's the correlation. So this is the correlation between what you expect and what you actually find. And if you square that, then you will get the explained variance. Almost done. So, is this the case? Is the outcome, is that actually equal to the model plus the error? So, this is a logical test. So, the double equal sign here actually tests if this is the same as that. So in our case, that's absolutely true. We see what the outcome really is, and if we add the model plus the error, then we get the same value. So the statement that field always makes in the book, it's actually true, right? It always is. Now visual, in terms of explained variance, what I've done here again is plot all the individuals on the x-axis, and plotted on the y-axis it's the study outcome. So if I calculate the average of the study outcome, I will get the horizontal line. That's the average. And I plotted all the data points in black. So the black ones are the data points, here and here. So the total amount of variance that there is to explain is the distance between the data points, the actual scores of the study outcome, and the average. And our model predictions are the orange circles here, and that is what our model predicts the study outcome to be. And here again, we can see how far we are off, what the error is, by the difference between our actual score and what the model predicts, which is indicated here with a purple thick line. So if we square the purple lines and add them all together, we have the sum of squares of the error. If we look at what the model explains to the average, we have the sums of squares of what is explained in the model, so the explained variance. So this is how the explaining of variance relates to what we've been doing in the previous blocks. It's just the same thing. We have a model that predicts something, and we can determine how well that predicts something to see how far we're off.
The blue part is the model, right? Then
the blue line is the line from the
explained variance.
No, the blue line is the line from the. I think I should make a better plot next time. It actually goes up all the way to the data points. So the blue lines are is the total amount of variance. Oh, so that was not supposed to happen. Are you still there?
Yep.
There's a button on my keyboard which makes my computer go to sleep. So if I push that one, my computer goes to sleep. I'm still here. Yeah, in the sense, I plotted, I created blue lines from the actual mean to the actual data point, but you can't see it because it overlaps sometimes. And in that sense, the distance between the orange circle and the average is the explained part, and the distance between the orange circle and the black circle is the unexplained part. So in that sense, you're right, and I think I don't see any overshooting of the model. So I don't see any cases in which, yeah, this one. Oh, yeah, this one, for example. This one overshoots, you see? So you have the distance from the average to the actual data point. So that is the total variance, or at least a part of the total variance. We have our model. So that is the distance between the average and what we actually expect based on our model. And we go back to the actual score, so this is our error. So that's the way you should see it. Does that make sense?
Yeah.
Okay.
I have a question.
Go ahead.
Would you say, like, I see a lot of thick purple lines, so the unexplained parts are, would you say that's high, or?
No, not really. Actually, because look, this one is a lot of unexplained variance. So the actual score is here, and I expected the total opposite. So there's a lot of unexplained variance here. But the rest, well, they're all very small bits, and we have. So I would say that the unexplained variance is low, and if you square these distances, the purple parts, if you square it, and and add those all together, then what you get is what is in SPSS shown here. So this is the amount, the sums of squares of the residual of the error for this model where, well, both are in. So
the blue part would be the regression sums of squares.
So the purple part would be the unexplained sums of squares, and the distance between the average, the total average, and the orange circles would be the explained part. So this is, in our regression model, the sums of squares. And that's this part. Right. Yeah. Good. Okay. So I think we're almost done. Let's see. So this explained variance part is defined by the sums of squares of the model in relation to the sums of squares of the total, which of course, if there's a lot to explain, so if there's something to explain and you explain a fraction of that, putting that in this order will always give you a percentage, right? So that is how this is, how the r squared is related to this. So I've said earlier that if you correlate your expected model outcome with your actual outcome and you square it, we call it the explained variance. So what I'm doing here is just, well, looking at that, well, if I correlate the study outcome with the model expectations and square this we call the explained variance, which is 75%. But this is exactly the same as putting the sums of squares of the model over the sums of squares from the total. So it lands you the same number because it actually is doing the same. And this is how this where your explained variance term comes from. We're explaining again a part of the total variance by our model. Okay, that is the end for now. Still alive?
Just.
Barely.
Just, yeah, barely. Okay. Let it sink in. You'll start with the weekly assignment. We'll practice this. We'll also cover this in the tutorials. And I wish you the best of luck with the weekly assignments. See you next week. I'll stick around for some questions. Bye, everyone.
Bye. Thank you.
Bye. Thank you.
Bye.
Hi, Sharon. I have a more general question. I quickly ask